It's my pleasure to introduce Ananth Shankar from the University of Wisconsin-Madison, and he's going to speak about abelian varieties that are not isogenous to Jacobians.
First of all, thanks so much to Payman and Kumar for inviting me. It's like a real pleasure to be speaking at your seminar. So as Payman said, I'm going to be talking about abelian varieties not isogenous to Jacobians, and everything that I talk about is joined with Jacob Zimmerman. All right, so let me sort of start with some setup. So let's start with a field that's algebraically closed. So it's a folklore question that dates back to possibly Katz or Oort that asks the following question. So given an algebraically closed field, can you find an abelian variety that's not isogenous to a product of Jacobians? So for the rest of the talk, I'm going to always mean product of when I say Jacobians, but I won't sort of keep saying it. So the product of will be implicit. Right. So the question is, can you find an abelian variety over an algebraically closed field that's not isogenous? Namely, there's no surjective homomorphism with finite kernel to a product of Jacobians from your abelian variety. All right. So for small dimensions, if you take the dimension of your abelian variety to be 1, 2, or 3, then every principally polarized abelian variety is in fact not just isogenous but isomorphic to a Jacobian. And given that every abelian variety is isogenous to a principally polarized one, that answers the question very easily for small dimensions. Now, what about 4?
So Ananth, in that case, it's
Yes.
not even product. You don't need a product, right?
So maybe we have to be a little careful, Kumar, because for instance, if you were to take a surface that's isomorphic to E1 cross E2, then the curve that you take might have to be singular. And that's why I want to say product of Jacobians.
I see. Okay.
But no, you're absolutely right. I mean, morally speaking, yeah, the product is an extremely cosmetic condition to impose. I just, want to work with the closed locus, not the open Tourley locus.
Also, could you just remind us quickly the dimension of the spaces of abelian varieties and the space of curves?
Perfect. In fact, let me do that right away. So for G at least 2, the dimension of the moduli space of abelian varieties is G. Well, this is G at least 1. This works for G at least 1 as well, but doesn't work for curves. So for G at least 2, the dimension of AG is G times G plus 1 over 2. And the dimension of MG, namely the moduli space of curves, is 3G minus 3. And so for G equal to 1, 2, 3, these are equal. And so because that's the case, every abelian variety of small dimension will be isomorphic to a Jacobian. But once G is 4, the dimension of AG is 10, and the dimension of MG is 9. So once G is 4, then, well, maybe you can find abelian varieties that are not isogenous of Jacobians, because the question, the question isn't answerable just for dimension reasons. In the sense that just by staring at dimensions, it's not obvious that every abelian variety is going to be isomorphic to a Jacobian. And so once G is 4, the question starts being interesting. So what I'll do is we'll talk about this question for G at least 4. All right. So I just specified a random algebraically closed field. I haven't said anything about what the field can be. So now let me start specializing to certain fields to see whether the answer is going to be easy or not in certain specific cases. So what happens when the field is the field of complex numbers? Well, in that case, the answer is quite easy. You can always find an abelian variety over C with any dimension at least 4, which is not isogenous to Jacobian. And that's because the locus of the locus in AG parametrizing Jacobians up to isogeny is going to be a countable union of proper subvarieties. Proper meaning not everything. And therefore has measure 0. Well, you have all of AG, you have a measure 0 subset that you want to avoid. And of course, you can do that. Okay, so as soon as you're working with a field as big as the complex numbers, then it's very easy indeed to find abelian varieties that are not isogenous to Jacobians just by a measure theory argument.
And so, Ananth, in this case, then because of the measure theory argument, you can also get from this products as well, right?
Sorry, what do you mean by products, Kumar?
In other words, if all the Jacobians are a set of measure 0, then you can look at finite products will also be a set of measure 0.
Exactly right. Exactly right. Exactly right. And in fact, just to be extremely precise, the locus that's a product of Jacobians is just going to be contained in the closure of Jacobian locus. So you get reducible Jacobians by looking at the closure of the torally of the Jacobian locus inside AG.
So let me understand this. So you take the image of the Jacobian map.
Absolutely.
MG to AG, then you take the closure, and that gives you all products.
That's right. That's right.
Okay, I see. Good.
Absolutely, because products correspond to Jacobians of singular curves, so that's going to be in the boundary of MG.
Okay, interesting.
Right. Okay, so just a simple meta theory argument over the complex numbers tells you that you can find, in fact, most abelian varieties over the complex numbers will not be isogenous to Jacobians or a product as soon as your dimension is at least 4. So if someone would stop you in the street and give you a random complex abelian variety, chances are it's not going to be isogenous to Jacobian. All right. But the field of complex numbers, it's like a pretty large field, infinite transcendence degree and such like. Is it possible to find smaller fields? Yes, sorry.
So, sorry for interrupting, Ananth. Even for complex numbers, do we know an explicit abelian variety that is not isogenous to Jacobian or a product to Jacobians?
Peyon, that's a fantastic question. I want to say, well, okay. Okay, so maybe the next thing that I say will answer the question about explicit. But by explicit, if you actually mean equations and such like, then I'd say maybe not.
Still equations, but like some abelian variety that we know it has like precisely been defined somehow, and we know that it's not isogenous to the product of Jacobians.
Great. So I think what I'll say next will hopefully answer your question.
Okay, thanks.
Awesome. So we've dealt with C. Now, what about maybe smaller fields? So okay, so let's deal with the case when K has transcendence degree at least 3G minus 3, strictly bigger than 3G minus 3, and that's because 3G minus 3 is the dimension of the Jacobian locus. Great. So why are we done? Why can we find an abelian variety over such a K that's not isogenous to Jacobian? Well, if you take any curve over K, it's going to be defined over a subfield K0 contained in K, where K0 has transcendence degree at most 3G minus 3. And that's because the dimension of the Jacobian locus is 3G minus 3. All right. And so if you can pick an abelian variety over K such that the smallest field of definition has dimension bigger than 3G minus 3. And why can we do this? Well, we can do this because the dimension of AG is bigger than 3G minus 3. Then such an A will not be isogenous to a Jacobian. Because if it were, then it would be defined over a smaller field. So Payman, here's maybe an answer to your question. If you were to, for instance, just pick a K-valued point of AG where, K has big enough transcendency, then such a point will indeed not be isogenous to Jacobian. For instance, you could just pick K to be the function field of AG, which has dimension 3G minus, which has dimension G times G plus 1 over 2, and pick A over K to be generic. In other words, I'm just suggesting that you pick the generic point of AG and pick the abelian variety over the generic point of AG. Well, that's not going to be isogenous to Jacobian.
I see. Nice, thanks.
Absolutely. Great. So, if your field is big enough, then just by playing either some measure theoretic games or by observing that the dimension of AG is bigger than the dimension of MG, well, you can always find an abelian variety that's not isogenous to a Jacobian. Now, what about smaller fields? So what's the smallest algebraically closed field in characteristic 0 that we can think of? Well, it's just the algebraic closure of Q. So in this case, none of these methods are going to work. Nonetheless, it's a beautiful theorem of Chai and Oort, who proved that the André-Oort conjecture for AG tells you that you can find an abelian variety over Q bar that's not isogenous to a Jacobian. And I'm going to sketch the proof in just a minute, but unfortunately, I think this proof isn't really constructive because André-Oort is not really constructive. It's like, well, maybe the word I should be using is André-Oort is not really effective yet. So, all right, how do you find an abelian variety over Q bar not isogenous to Jacobian? Well, so a very natural class of abelian varieties to think about is a class of CM abelian varieties, and that's precisely what Chai and Oort do. So, in fact, they prove that not just can you find an abelian variety, they prove that you can find a CM abelian variety that avoids the Jacobian locus up to isogeny. So here's their method. Suppose you take the TG, which is the closure of the Jacobian locus. It's a proper subvariety of AG. It's not everything. So what we need to do is we need to find a point that's not isogenous to any point of TG. All right. So the nice thing about CM, one of the nice things about CM points is that the property of being CM is a property that's preserved even after modifying itself by isogeny. So suppose we were to take the set of CM points. All right. Of CM Jacobians. So the André-Oort conjecture for AG tells you that the Zariski closure of the set of CM points is going to be a finite union, and the finiteness is key of Shimura varieties. Well, once you have a finite union of Shimura varieties, it's easy to find CM points that avoid sigma bar up to isogeny. So here's how China would actually implement this part of the argument. What they do is you take your list, and suppose your list is S1, S2, up to Sn. Well, consider, so all one has to do is they pick a totally real field with Sn Galois group with full Galois group pick a totally real field F with full Galois group such that the Hilbert modular variety parametrizing abelian varieties with real multiplication by F isn't in the list S1 through Sn, and then pick a CM point whose totally real field is F. Now, here's why that's going to work. The property of CM points whose totally real field has very large Galois group. A very nice property is that the only positive dimensional Shimura varieties that contain such a CM point will be the Hilbert modular variety and AG itself. So if your CM point lies in S1 through Sn up to isogeny, that means that one of S1 through Sn has to be the Hilbert modular variety associated to F, but we've assumed that's not the case. And therefore, your CM point is not going to lie on S1 through Sn up to isogeny. And there you have it. You found an abelian variety that is indeed not isogenous to a Jacobian. And crucial to the proof is the fact that if you were to take the set of CM points in AG and take the Zariski closure, that's going to be a finite union of Shimura varieties. That's extremely important to their proof. Without this fact, their proof won't go through. So this is the main idea in their proof. So once this is carried out, you can find an abelian variety not isogenous to Jacobian over Q bar. But of course, the proof uses the Andreot conjecture. All right, so now might be a good time for me to pause for questions if there's any.
Yeah, Ananth, let me just try to understand now. If I take a Shimura variety.
Yes.
Okay, so I have finite element. Let's say I even have just one. Let's say even one of the SI is in fact another Hilbert modular variety, corresponding to some real quadratic, totally real field.
Absolutely.
Then the CM points will correspond to CM quadratic extensions of F. Is that right?
That's absolutely right. Yes.
It can't be any other thing. It must always contain F. Is that right?
Exactly right. That's exactly right.
Okay, so that's why. So I see. So therefore, you're using here implicitly that if I give you a Shimura variety, it's in a list of possible Shimura varieties, and I know the possible totally real fields that can occur.
That's exactly right.
In any CM point on that Shimura variety.
That's exactly right. That's exactly right.
I see. Okay. Yeah.
And then you just have a finite list of totally real fields to avoid, which can easily be done.
Yeah.
Great. Thanks very much for the comment. All right. So that's what China-Notes proof does. I should remark that CM abelian varieties in some sense are rare and they have very small monodromy. So what China-Note have done is they're like giving you sort of abelian varieties not isogenous to Jacobians with very small monodromy. And Well, one might also want to find abelian varieties with maximal monodromy that are not isogenous to Jacobians. And I'll later talk about this question. All right.
So you sort of
yes.
you sort of said something like that right before, because when you take a generic point, it's likely to have you remember you had a genericity argument before?
Exactly right. Exactly.
That will have maximum monodromy.
Exactly right. That's absolutely right. But of course, because it's like a generic point, it's not going to be Q bar.
Right.
So it's still an interesting question to find something over over Q bar, or like over a number field that has maximal monodromy and yet is not isogenous to Jacobian. Great. So, but before talking about that, let me maybe reinterpret this question about Jacobians in terms of arbitrary subvarieties of AG. This, in fact, I think this reframing of the question is due to Poonen. So the fact that, okay, so where did we use the fact that we have the Jacobian locus? Absolutely nowhere. The same proof would have gone through if you had any subvariety of AG that wasn't everything, because you could just take the CM points contained in that subvariety, take its Zalski closure. That's still going to be a finite union of Shimura varieties. So the fact that we're dealing with the Jacobian locus is actually not very important. So here's Poonen's framing. Suppose you have D contained in AG is any subvariety. In fact, divisor is going to be, in fact, of course, like, the problem will follow from the case of divisors. But suppose you have any subvariety, then the question is, does there exist a k-valued point of AG that's not isogenous to any point in your divisor? And of course, if k is Q bar, the exact same proof works. All right. Well, this takes care of characteristic zero fields. You just care about algebraically closed, and as if now you're not too interested in monodromy. What about characteristic T fields? So, first of all, Andreot is just doesn't hold mod P. And therefore, Chinote's proof just doesn't have a chance to go through at all. Not just that, we expect different behavior over FP bar. So if your field is FP bar, namely the smallest cat P field, then heuristics that Jacob and I developed, in fact, I think Poonen independently had similar thoughts, suggest that the answer is different. So here's what we think. So here's roughly a heuristic and why we think the answer should be different. Let's assume that D has maximal monodromy. Assuming extremely expected conjectures, this should imply that the only Shimura variety that contains D is AG. So if D has maximal monodromy, well, we have a map from D of FQ to the set of isogeny classes defined over FQ.
So sorry, D is still a divisor inside the AG?
No, so D is right now subvariety.
Subvariety of what?
Of AG.
Of AG.
D subvariety of AG.
Okay.
And the question is, can you find a point of AG that's not isogenous to any point of D?
Okay, and by monodromy, you mean the action of Gao or something on the cohomology of D?
Another way to say it is we have your universal family of abelian varieties over AG, which we can pull back to D. And so you can look at the family of, say, aladic Tate modules on D, and just look at its monodromy.
Yeah, that's the same thing.
Perfect. Absolutely. Great. So the cohomology of the universal family that should just have maximal monodromy. Great. All I want to say actually is that D is not contained in a Shimura variety of that's not equal to AG. And this condition definitely forces that, but even in general, the same thing should go through even if your D is not contained inside any other Shimura subvariety of AG. So either way, whether or not D has maximal monodromy, you have a map from the FQ points of D to the set of FQ isogeny classes of abelian varieties. And our heuristic is that if D has maximal monodromy, then this map should be a random map. Okay. Now, if you were to accept this heuristic, then we know exactly how many points D is going to have. And it's also easy enough to count the number of FQ isogeny classes by using the fact that FQ isogeny classes are parameterized by WQ numbers. So it's easy to bound the number of FQ isogeny classes as well.
This is Honda Tate, isn't it?
Exactly right. That's exactly right. Exactly Honda Tate. And the point is, once the dimension of D is bigger than half the dimension of AG, we expect the random map to be surjective. As Q goes to infinity. And therefore, we expect that every abelian variety with dimension less than or equal to 9 is abelian variety over FP bar with dimension less than or equal to 9 is indeed isogenous to a Jacobian. Just to be careful about Newton strata and such like, so this map, we expect it to be a random map when we restrict it to every Newton strata. Let me just say ordinary, just to be safe.
Sorry, where did the 9 come from?
Because if G is 9, then the dimension of MG is bigger than half the dimension of AG. And if G is equal to 10, then the dimension of MG becomes less than half the dimension of AG. So it's exactly 9 to 10 where you sort of cross the threshold of being less than half the dimension to bigger than half the dimension. And right. And so like just doing this simple count suggests that the answer of FE bar is very different. And Jacob and I also have an example to support this conjecture. It's not in the context of abelian varieties and Jacobians, but in the context of this more general question of a subvariety of a G and a point inside there. And in fact, we're not even going to work with AG, we're going to work with the product of modular curves because that's where our example works. So we have the following example. So for n large enough, in fact, our bound is 270 for what it's worth, we construct an explicit divisor such that every point, FP bar valued point of the divisor is isogenous to some point in the divisor. So I should have said every point of A1 to the n is indeed isogenous to some point on the divisor. And needless to say, this does not happen in characteristic 0.
So this seems to be going the opposite direction now.
Exactly right. That's exactly right.
And the heavy restriction is that you're looking at a product of modular groups?
That is correct. That is correct. We still expect the same theorem to be true even for AG. It's just that we can't prove anything yet.
Oh, I see. So actually, you're expecting the thing to be completely false in the case of FP.
Exactly right. Like as soon as your subvariety has dimension bigger than half the dimension of AG, we expect every FP bar valued point of AG to be isogenous to some point of D.
Mm-hmm. So, but in this theorem, do you still have the hypothesis on the dimension of D?
Right. So D ends up being a divisor.
D is a divisor. Divisor.
Yes.
Got it. Mm-hmm. Yeah,
Absolutely.
You have that. Yeah, I see. Yeah.
Yes, indeed.
Mm-hmm.
And and the interesting part is Andreo tells you that this can't happen in characteristic 0 over Q bar. So this is genuinely different behavior than what one sees in characteristic 0.
Interesting.
Great. So that is what we now expect over FP bar. Well, what about other characteristic P fields? For instance, what about global function fields? So in other words, K is the algebraic closure of some field of transcendence degree 1 over FP. And now let's take D contained in AG to be some divisor. And our first theorem is that the function field case behaves like the number field case and not the finite field case. So what we prove is that there does exist a k-valued point of AG that's not isogenous to any point of D. Okay. We also reprove the theorem. We find a different proof over Q bar. But now our point we can prove has maximal monodromy. That's not isogenous to any point in D. And finally, we prove a partial statement over FP bar. So of course, we expect that every FP bar valued point of AG will be isogenous to some point of D. But there's still something that we can say. So what we can say is that there exists a point in AG of FP bar such that if you were to take any Hecke translate of that point, then as a set that's not going to be contained inside D for every prime to P Hecke operator. Ideally, we'd be able to prove, if the finite field behavior was the same as the number field behavior, which it's not, then we'd want to prove that tau of x intersected with D is empty for every tau. But we expect that to not be true anymore. But we can prove that your tau of x will not be contained inside D. So even though some points might be isogenous, 2 points in D, even though some points in D might be isogenous to x, an entire isogeny orbit will never be contained inside D for any Hecke operator. All right. So for the rest of the time that I have, I will sketch the proofs of theorem A and theorem B. And want to see the proof of theorem B, it'll hopefully be clear how you prove theorem C as well.
Ananth, can you remind me, in the case of your last theorem, there's theorem C.
Yes.
What is there's a result, isn't it, of Choi perhaps, which talks about density of Hecke orbits?
That's a fantastic question. Yes, indeed. Chai proves that if you were to, absolutely. So Chai proves that for AG over FP, then the union over all tau of X is Zariski dense if X is ordinary. And but of course it's possible that like a certain Heck operator of, if you just take one Heck operator and you evaluate it on X, you're just going to get a finite set. So of course a priori that could be contained in D, even though the whole union is going to be Zariski dense.
Got it. Thanks.
Great. But no, but you're absolutely right. Like Chai's theorem suggests that well, theorem C should be not very difficult. Absolutely. Chai's theorem strongly suggests the truth of theorem C. Great. So here's the idea. Okay, so what I'm going to do is I'm going to first sketch the proof of theorem A, then I'll move on to B if time permits. So here's the idea of proof of theorem A. And it's, as you'll see, actually quite simple. So for simplicity, let's assume that D is smooth. So for the Torelli locus case, that's fine. Even in general, we don't really need this assumption because once you fix a variety, how singular it is always going to be bounded. But anyway, for simplicity, let's assume that your divisor is smooth. So it's enough to show, so using the curve function field correspondence, it's enough to show that there exists an irreducible curve such that every irreducible component of tau of C is not contained in D as we range over all Heck operators. Okay, so dealing with every irreducible component of tau of C could be annoying. So we construct C such that C has maximal monodromy. This tells you that tau of C is going to be reducible. And therefore, instead of dealing with the reducible components of tau of C, we can just deal with tau of C itself. So it's enough to show that tau of C is not contained in D for all Heck operators tau. Well, now how do we? Yes.
What is that? Why is that implication? So C has maximum. C is a curve.
Yes, that's right. C is a curve.
C is a curve, maximum monodromy. Then why is the Heck image reducible?
So here's a function.
Okay, I got it. I think because the monodromy commutes with the Heck action, isn't it?
Exactly right.
Oh, okay.
Exactly right. And so for instance, if you were to start off with an abelian variety over Q that has maximal monodromy, then if you were to take tau of X, then all the points in tau of X will be in one Galois orbit. Therefore, it'll be like 1K valued point. Great. So it's enough to show, like, if you were to construct C that has such that it has maximum monodromy, it's enough to prove that tau of C itself is not contained in D. Now, how do we insist on this? So the idea is to construct C such that C is highly singular at some point in C, and such that tau of C is also going to be highly singular at tau of P. Now, if your curve is extremely singular at a point, then your C can't be contained in D, as D is smooth. If the tangent space of C equals the tangent space of AG, now for prime to P Heck operators, your Heck operators are étale. In other
Sorry,
words,
why do you need this last condition? I mean, so if you had a singular C,
right?
Inside D if you had a singular C, it cannot be contained in D.
If your C is extremely singular, so I haven't been too precise about what very singular means, but in particular, if at your point the tangent space of C is everything, then it can't be contained in D, because the tangent space of
Go ahead.
Just because the tangent space of D is codimension 1 inside the tangent space of H.
Yeah, but if it's highly singular, doesn't it cut down the tangent space?
No, the tangent space goes up.
It goes up. Yes, that's right. Okay.
Sorry. Absolutely.
I see. Yeah. Okay.
And right, so so if your goal was to find a curve not contained in D, well, this does it for you. But the annoying thing is you need this condition to also be preserved upon taking Hecker translates.
Yeah.
And that's why the fact that your curve has maximal monodromy and therefore tau C is reducible is extremely useful, because instead of a priori, what could happen is tau C could also be very singular, but it could be singular because you have different irreducible components all meeting at a point. And the fact that C has maximal monodromy says that this can't happen, because it tells you that tau C has to be irreducible. Great. So if you work with prime to P Heck operators, then these are going to be étale, and therefore these preserve the local structure of C, and so tau of C will also be highly singular. And so we get that tau of C is not going to be contained in D. Okay, and in fact, this finds a curve over Q or Q bar, none of whose Hecker translates are contained in D. But because we're working in characteristic P, we also need to deal with P power Heck operators. Or P power Isogenous. And these are not étale. So it's not quite as straightforward to say that the P power Hecker translates of C will also not be contained inside the Torley locus or inside D. Okay, so how do we deal with the fact that the P power Hecker operators are not étale? Well, we have two inputs. The first input is the fact that one can understand the local behavior of the Hecker operators using set-8 coordinates. So set-8 coordinates at ordinary points. Using these, one can understand the local action of p power Heck operators at ordinary points. In particular, here's what happens to be the truth. There are distinguished tangent directions that come from the set 8 coordinates. And these tangent directions span the tangent space of AG. And here's what ends up happening. So you start off with your base point X, and supposing you take of these distinguished tangent directions. Then, if you were to apply a p power Heck operator to X and these tangent vectors, well, suppose you get 2 points. Ideally, we'd have that both these tangent directions propagate to both these points, but alas, we don't. But what actually happens is one can, depending on the shape of your Heck operator, one can see that one of these tangent directions will propagate to one point in the forward image of X, and the other tangent direction will propagate to the other point in the forward image of X. So this is not good enough because it doesn't give you, because a priori doesn't give you anything singular. However, one can actually play this game backwards. If you were to start off with the point Y, and if you were to start off with 2 tangent directions at Y, 2 of these distinguished tangent directions at Y, and given a Heck operator tau, if you look at the backward orbit of tau, and suppose you have 2 points in the backward orbit, let's say x1, x2, then you can always find this sort of a picture. Namely, you can always find 2 points in the backward orbit and 2 tangent directions at those 2 points, where the first tangent direction maps to the first one at Y, the second tangent direction maps to the second one at Y. But then, for things to go through, you would want your C contain the backward orbit and of Y and your tangent directions under all p power Heck operators. And well, this looks impossible, right? Because this looks like you're imposing infinitely many conditions while constructing your curve. And why is it at all possible or feasible that you can find a curve that satisfies these infinitely many conditions? Namely, it has to contain the backward orbit of your fixed point Y and the tangent directions for every single Heck operator, for every single p power Heck operator. So how do you ensure that this happens? And well, our second idea is to use hypersymmetric points. So the beautiful thing about these hypersymmetric points is that a point is defined to be hypersymmetric if it's isogenous to a self-product of elliptic curves. And the amazing thing about hypersymmetric points is that the forward and therefore backward orbit of a hypersymmetric point and p power Heck translates it's extremely crucial that these are p power Hecke operators, is always going to be finite. And that's because and the way one sees this is that if x is e to the g, and if y isn't, and let's say x is defined over f cube, and if y is an element in the p power Hecke orbit of x, then y is also going to be defined over f cube. So one can cut down from infinitely many conditions to finitely many conditions by just insisting that your point y is hypersymmetric, because then the backward orbit of y under p power Hecke translates is going to be finite. It's just going to consist of points all defined over f cube. So it's enough to ensure that C has maximal monodromy and C contains some hypersymmetric point y, its p power orbit, all of which is just finite, and the set-ate tangent directions at these points. And that's it.
So, Ananth, are you still? I'm a little puzzled. Are we still in the context of something contained in the power of a modular curve?
Oh no, I'm sorry. This is an AG. This is in the context of AG.
AG, okay.
Yes. But the same proof will go through even in the case of the context of something contained in the power of modular curve. Well,
I mean, just thinking that in the context of modular curve, that CM points tend to have this hyperspecial property.
No. So the thing is, we're working over FQ. And no, you're absolutely right. So we're working with FQ, so every point is going to be CM. And yes, in the context of a modular curve, every point is indeed going to be hypersymmetric, were you define hypersymmetric appropriately. You're absolutely right. Like if you look at diagonal isogenies, then everything diagonally isogenous to an ordinary product of elliptic curves will be defined over the same field. You're absolutely right. And the same thing goes through even AG if you were to work with a self product of an elliptic curve. It's exactly the idea that you have in mind. It's exactly that. Great. So yeah, so so using this trick with hypersymmetric points and asking for your C to have maximum monodromy and for it to be singular enough, then one can find the C, which isn't contained in D up to isogeny for every Hecke translate. And that solves that proof theorem A. Let me very briefly sketch how we prove theorem B. So first of all, we construct a curve over Q that has maximum monodromy. And not contained in D. Up to isogeny. So then how do we go from this curve to a number field value point? Our idea was to use intersection theorem. So if we find a large degree point on C that has maximal monodromy, then if, let's say the large degree point is X, then if tau of X intersected with D was non-empty for some tau, then one has that tau of x has to be contained in D by maximality of monodromy. And in fact, and tau of x will be a point with degree equal to the degree of x multiplied by the degree of tau. On the other hand, tau of x is clearly contained in tau of c, and one can bound this intersection number in terms of the degree of tau multiplied by c intersected with d. In fact, this should be an equality. So the fact that your point is contained in a curve with maximal monodromy and such like gives you an upper bound for the degree. This gives you an upper bound for the degree of tau of x. But then assuming that tau of x is contained in D contradicts this lower bound, contradicts this upper bound. So the point is, we have that the intersection of tau of c with D has to have degree less than or equal to degree of tau times c intersected with D. But the degree of tau of x is going to be quite large. It's going to be the degree of x multiplied by the degree of tau. So as soon as the degree of x is bigger than c intersected with D, we get a contradiction, which stems from assuming that C is not contained in D up to isogeny, C has maximal monodromy, and so does X. So I apologize. So this part has been like extremely vague, but I'm out of time. So let me stop now. If there's questions about this part, I'd be more than happy to address them then. Thanks very much for your attention.